Hi, today we cover the topic in circular motion. So, a body can travel through a circle if it is attached to a piece of string held over here at this point, and then you swirl it around in such a way that it goes around in a circle. Let's assume that this is at position 1, and at some point it would be here at position 2 as it travels along the circle. So this would be the center of the circle. So this would be the radius, and the distance it has covered would be the arc length of the circle. We denote it as S, arc length. So the arc length is defined as S equal to the radius multiplied by the angle over here as it moves. The angle is called the angular displacement. So it is an angular displacement. So it is theta times r. So to find a definition of what is the angular displacement, so we can replace this in the equation by 1. So we say that this is 1 radian, and if this is 1 radian, so by definition a radian is the angle subtended at the center of a circle by the arc length, which is S, which is equal to the radius of the circle, which is r. So by definition, we can define 1 radian. 1 radian is defined as the angle subtended at the center by an arc length equal to the radius of the circle. So this is a definition for 1 radian. If you want to define a radian, you can just define it as the angle subtended at the center by an arc length equal to the radius of the circle itself. So now you know that S equal to R times angular displacement. So let's assume that the particle has covered a whole circle and goes around and returns to the same point as it were before. So if it has covered the whole circle, you know it is a circumference of the circle, which would be the distance covered, which is S. So this is 2 pi r, and the circumference is just the distance S covered. So we can replace S in the equation by 2 pi r. So 2 pi r is equal to r theta. So r cancels, and you will get theta to be 2 pi. So in order to complete a whole circle, the angle has to be 2 pi radian. Okay, we call it 2 pi radians. So now you know in degrees a whole circle is 360 degrees, but in radian it is just 2 pi. So 360 degrees is just 2 pi radian. So if I want to find 1 degree, it is 2 pi divided by 360, which is pi over 180. So 1 degree is equivalent to pi over 180 radian. So you can convert from degrees to radian and from radian to degrees. So to convert from degrees to radian, So we just have to multiply by pi divided by 180. Okay? So if you want to convert from radian to degrees, you have to multiply by 180 over pi. So it's just the change in the numerator and denominator. Okay? So now we have to look at a very important terms in circular motion, which is called the angular speed or angular velocity. So these two are different. Okay, speed is a scalar and velocity is a vector. So for this angular speed or angular velocity, we use the symbol omega to define this. So the unit is radian per second. Now what is angular speed or what is angular velocity? So if an object goes around in a circle, let's assume it is traveling in this direction. At some point it would be in this direction. Okay, this is the angle theta and this is r. Now we define angular speed to be in this direction. So it is in this direction, in the direction of the angle. Okay, so it is the angle that has been covered per unit time. So the angle is in radian. So omega is equal to the angle covered divided by the time it takes to complete this, to complete the path. So this is in radian and this is in second. So the unit is radian per second, and therefore you can see how we arrived it at here. So now to define the angular speed, it is just defined. So for angular speed, it is defined as the angle swept out by the radius per unit time. Okay, it does not have a direction because it is scalar, whereas angular velocity, we can define it in a specific direction. So we can say that it is just the angular speed in a given direction. So these are the two definitions that you need to know. So now we have to introduce you how omega, the angular speed, is related to the velocity of the particle, which is v, and how it is related also to the radius of the particle. So let's assume that a particle again is traveling through a circle. It has a radius r. It travels a small distance. Let's assume it is very small, that this is d theta and the displacement, the arc length, is ds. And it has covered this in a time dt, which is very small. And this is r. So assuming this, now I can write omega, which is the angular velocity, to be the d theta, the change in the angular displacement, divided by the change in time. Okay, it's just like this, but instead we have very small angular displacement and very small time. Now, this is another definition So if you want to find angular speed at a point, you just differentiate the angular displacement with respect to time. Okay, now we know that this speed is always in tangent to the circle. So it is always changing. Sorry, the velocity is changing, but the speed is constant. So now, from the definition that we already know, that theta is the arc length divided by the r. So r is a constant. So if we differentiate, you know that there's a small change in theta and there's a small change in the arc length. So the radius is the same, it doesn't change a thing. So now if I have to differentiate with respect to time, I will get the angular velocity. So let's differentiate with respect to time. We'll differentiate both with respect to time. So d theta by dt is equal to ds divided by dt. This is a constant, I can put it outside. And this is omega. ds by dt will give you the speed of the particle, because it is the change in the arc length divided by the time. So it is 1 divided by r times the velocity of the particle, and this velocity we can write it as omega r. This is another definition for velocity in terms of omega and r. So remember that the radius of a circle is always a constant over here. Now let's relate angular speed with the time. So we know that in a circle, the particle would be covering the distance s theta. So this is r. Now let's assume that theta is now 2 pi. So it has covered a whole circle. So if I want to know the time period, t is a time period. So time period is when the particle has completed a whole rotation. So this is called the time period. So now omega is theta divided by t. So theta is 2 pi and t is a time period for the particle. So omega is 2 pi divided by the time period. Okay. Now we can relate this to the frequency, because you know that frequency is the number of rotation per unit time. So it is given in units of hertz, or 1/second. Okay, so now we can replace 1/time by the frequency. So this is 2 pi times the frequency. We get the omega, the angular speed. In terms of f, the frequency, and in terms of t, we can calculate the angular speed. Now let's talk about the direction of the particle's acceleration and the force, and also the velocity of the particle. Now let's assume the particle is traveling again through a circle. So this is the radius. At some time it will be here. So it has covered a angular displacement of theta. This is r. So assume that this is at position A and this is at position B. And at time t is equal to 0, the particle is traveling with a velocity v with a little subscript a. And this at point B, it is traveling at a velocity v, b, and this is at time t is equal to t1, for example. Okay, now we consider this particle of mass m moving around in a circle of radius r at constant speed. So in moving from A to B, so you can say that in moving from A to B, the change in the velocity would be Vb minus Va. So this is just like vectors, addition and subtraction of vectors. So we can add minus Va. So it is just like we are adding two vectors or we are subtracting a vector. So you know Vb is in this direction. Vb is in this direction. Here you are. Plus minus Va. Va is in this direction, but the minus Va will be in the opposite direction. So this is Va. Now, where is the resultant, the change in velocity? It is here. So this would be the change in the velocity. So and remember that a change in velocity is acceleration. And the change in velocity is directed toward the center of a circle. Remember the delta V is directed toward the center of a circle. Okay, so the change in velocity is acceleration. Therefore, the acceleration is also towards the center of the circle. So this is called the centripetal acceleration. Let's call it with a small subscript c over here. So the centripetal acceleration would be always directed towards the center of the circle, because the change in the velocity is towards the center, and therefore the acceleration is towards the center. It can also be proved that the magnitude of the centripetal acceleration is given by v squared over r. But the derivation is not in your syllabus, so we can just ignore this. Okay, so you just have to remember that A is just v squared divided by r. Okay, but also you know that v is r times the angular speed, and therefore A is, you can replace v into this equation, or omega to the square divided by r, which will give you r omega square. So this is also a formula for centripetal acceleration. Now you know that by Newton's second law, the force is equal to the mass times the acceleration. So if the acceleration is directed toward the center, meaning that the force also would be directed toward the center of the circle. And now we give this a new name. We call it the centripetal force, and this would be the centripetal acceleration. And the mass is just a constant. So remember, if you want to find the force, the centripetal force acting towards the center of the circle, you just have to multiply the mass and the acceleration of the particle. So now we continue it in the next part.